Hello and welcome to another video about multivariable calculus, Calculus 3. Today we will be going over the multivariable calculus of chain rule. So from Calculus 1 and 2, I am sure you are familiar with the chain rule. F times G prime plus F prime G, I believe. I'm sure you are more than familiar with that. You've probably done it a few times by now. But in multivariable calculus, it is a little bit different. Same concept, but it is different. So I guess the question of the multivariable version of chain rule is, what is it? Well, say we have some kind of function z is equal to f of x, y. Well, we can take partials of that. We can take double partials. We can take however many partials we want. But what if, for instance, our x was in some x of t, and our y was also in some other variable t, function of t. So that is essentially what the chain rule is what if we wanted to take the partial derivative of, let's say, t. So what we would do is we would essentially use the tree diagram. Is the easiest way for me to think about it. That is how we are going to do it. And that is what I am going to be teaching in this video today. So using this right here, we're not going to start off with any functions. First of all, we're just going to start off with some general idea of it. So, for example, say we have that function that stated prior, z is equal to f of x, y. But we have x of t and y of t, making it essentially f of x of t, y of t. So what are we going to do here? So we know that our x and our y are in terms of t, so they are functions of t. Whereas our z is function of x and y. Well, what is the tree diagram? Essentially, we start from the top and we go to the bottom. So, in order to find dz over dt, take note that these are not partials. In order to find this, well, what are we going to do? We are going to derive that formula with the tree diagram. So, starting off over here, we have the very top of the tree. That is going to be our z function. That is our output, our primary output. The two subsystems, the intermediate variables, so to speak, will be x and y. So let's go ahead and draw two little branches here of x and y. Well, these x's and y's are intermediate variables of the final independent variables, t, functions of t. Therefore, we have another one going to our final independent variables of t. Come on. Well, we want to do that. So, essentially, we have this dependent variable right here. We're going to label it. We have a dependent variable. We have intermediates, variables, and then we have the independent variables. Well, you may be asking, how do we take the derivative of z in terms of t? Well, what we're going to do is we're going to take partials from every route from z to t. So we have, with respect to x, we're going to take the partial derivative of z with respect to x this way. I'll use red. And down, we are going to take the partial of x with respect to t. Okay, well, let's do it for the other side. This way, we have taking the partial of z with respect to y. Now we are going to take the partial of y with respect to t. And what we're essentially going to do here is we're going to multiply these two and add them together. So what is our dz dt going to look like? It is going to look like the partial of z with respect to x here. We're going to go down our tree times the partial of x with respect to time. That's there. Going down the other side, we have plus the partial of z with respect to y multiplied by the partial of y with respect to time. So for our z is equal to f of xy, function of x and y, and our subfunctions, functions of time, we have a dependent, two intermediates, and one independent variable. That is the brief concept of what the chain rule is. In colloquially, we can say that it is the sum of all paths from z to t. So that's essentially what it is. Okay, let's dive into an example right now. Well, let's say we want to find, well, let's give the functions first. Z is equal to x squared minus 3y squared plus 20, wherein our x is equal to 2 cosine t and our y is equal to 2 sine t. Looks good. We want to find, we'll make our objective, find dz over dt. Well, it's the same concept. We're just going to go ahead and make a tree diagram. So what are we going to do? We are going to have our dependent variable up top. That is going to be our z, with two branches sticking out. Since z is a function of x and y, we are going to have x and y. And each of those functions are functions of time as well. So both of these have a little branch sticking out for t. I'm going to color code a little bit. Remember, this is our dependent. These two are our intermediates, and these two are our independent. So how are we going to do this? dz dt is going to be the partial of z with respect to x and the partial of y with respect to, partial of z with respect to y, I apologize. And then we are going to come down here where we have our partial of x with respect to time and our partial of y with respect to time. So putting this all together, our dz dt is going to equal the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. That is going to be our formula for our chain rule. So let's go ahead and calculate what our different parts are. So we have our dz dx, which is just going to equal d over dx of our function up here, x squared minus 3y squared plus 20. Recall in the last video, everything in here is held as a constant except for x, so this is going to equal 2x. Let's go ahead and solve our dx dt now. Dx over dt, which is going to equal d over dx of this function here, 2 cosine t. Well, just recall that the derivative of cosine is negative sine. That's really all we need to know because there's no other variables in here. So we have negative 2 sine of t. Looks good. Well, let's go ahead and do our dz dy now. that is going to equal the partial of z with respect to y of x squared minus 3y squared plus 20. Remember, everything held constant except for y. This is just going to equal negative 6y, power rule. Now we are going to calculate our dy dt, which is going to be the partial of y with respect to t, with our y being this function right here, 2 sine t. Recall that the derivative of sine is cosine, so we just have 2 cosine t. Putting all of this together, we now have dz over dt is going to equal what? Well, we have our dz dx times our dx dt, so this is going to be 2x times negative 2 sine of t plus our partial of z with respect to y times our partial of y with respect to t. So we're just multiplying those two, plus negative 6y times 2 cosine of t. This is going to equal what? Negative 4x sine of t minus 12y sine of t, cosine of t. Looks good. Now, what we are going to want to do, let's write a little note here. Turn our intermediate variables to their independence. So what I'm essentially saying is that this x right here and this y right here, we are going to turn into their respective functions. So our x is equal to 2 cosine of t. Therefore, we have negative 4 times 2 cosine of t sine of t minus 12 times our y function, which is going to be 2 sine of t. 2 sine of t, cosine of t. Let's go ahead and get rid of these right here. Looks good. So now it looks like we have negative 8 sine of t, cosine of t. I just like to put my sines in front of my cosines. Minus 24 sine of t, cosine of t. And as you can see, we can simply add these together, which is just going to equal negative 32 sine of t, cosine of t. That is going to be our final answer. That is how you use the chain rule in that kind of application. Well, I am going to do one more example. That is a pretty basic one. And realistically, we can have anything. So just as a quick little note here, we can do the tree diagram with, say, w is equal to a function of x, y, and z, wherein our x of t, y of t, z of t, simply we're just going to add another branch to this right here with our z, another t right here, and we are going to add a d, well, this doesn't really apply, I guess, but just make a new tree diagram just so that I can be clarified. We will have a tree diagram, this is going to be quick, of some w with 3 branches of x, y, and z, and each of these has their own t. So it's the exact same concept. We are going to take the derivative, the partial of y with respect to x, partial of w, with respect to z, partial of w with respect to y, partial of w, or partial of x. Don't rush like I am. I guess I don't really have to rush. Partial of y with respect to time, partial of z with respect to time. And essentially what we're doing here is we are just going to do the exact same process. We're going to go down this branch. We're going to go down that branch. And then we are going to go down. Oh man, did my pencil die? Nope. Going to go down that branch. We're going to go down this branch and we're going to add them all. So if we wanted, say, dw over dt, that would just equal our partial of w over respect to x times our partial of x with respect to time plus our partial of w with respect to y times our partial of y with respect to time plus our partial of w with respect to z times our partial of z with respect to time. That would be how you do it with multivariable. Assuming that we only have x of t, y of t, z of t, that is how you would go about doing that, just as a quick little note. I am not going to do a 3 intermediate variable one. I'm going to do one more example wherein we have a function z is equal to, let's say, xy minus x squared y, wherein our x is equal to a function of 2 independent variables. So we have x is equal to s plus t, and we have our y is equal to s minus t. Well, how would we do this? We were essentially just going to make 2 branches off of our x and y. I'm going to go ahead and demonstrate what I'm trying to say here right now. We have our top here, being our z value. We have 2 intermediate variables going down here. That is going to be our x and our y. And each our x and our y now have their own intermediate, or their own variables that they are functions of, s and t. Y, s and t as well. So how we're going to take this partial of dz dt, and we'll do dz ds here in a little bit. Well, we'll just mark it down right now. ds, we are going to take the partial of z with respect to x, then the partial of x with respect to s, partial of x with respect to time. Going over to the right side, we have the partial of z with respect to y, the partial of y with respect to time, partial of y with respect to s. So our dz dt, we're going to ignore these branches right here. So we have dz dx times dx dt plus, that's done there, dz dy times dy dt. That is going to be our partial with respect to time for y. That is dz dt. One more time, we are going to have dz ds, which is going to be ignoring the t now. Well, we're going to have dz over dx times dx over ds plus dz dy times dy ds. And that is going to be how we solve the chain rule for both of these respective things. For the sake of time, I believe I am only going to solve one. I want to solve, we'll go in terms of t, because that's what'll make it different. These two are going to be different, as you can see, but that might be a little bit of a spoiler. Well, we're trying to do dz dt, okay. dz dt, we require dz dx, which is going to equal the partial of z with respect to x. Well, haven't really seen these too often. I explained it very briefly in the partial derivative video, but just treat y as constant. So we are going to have y minus x squared, or 2xy. I apologize. That's dz dx. And our dx dt is going to be taking the derivative, the partial of this with respect to time. That is just going to equal 1. Now moving on to this aspect, we have dz dy, dz over dy, which is going to equal, take the derivative of that, that is just going to be x minus x squared. Finally, we have our dy dt, which is going to be taking the partial of this with respect to time. That is going to be -1. So we have all of our components together. We can now solve what dz dt is. Let's go ahead and do it. Well, dz dt is going to be the partial of z with respect to x, so that is going to be y minus 2xy times the partial of x with respect to time, that is times 1, plus the partial of z with respect to y, x minus x squared, times -1. There we go. Now we're just going to go ahead and simplify this a little bit. We have y minus 2xy minus x plus x squared. Go ahead and plug in our independent variables now. X is equal to s plus t, and our y is equal to s minus t. So we have s minus t minus 2 times s plus t, s minus t minus s plus t plus s plus t squared. This one is definitely going to be a little bit annoying to solve, but I'm confident that we can go ahead and do it. So let's go ahead and do it. We have s minus t minus 2 times s squared minus 2ts minus 2ts minus t squared minus s minus t plus s squared plus 2ts plus t squared. Let's go ahead and, oh man, this is definitely a little bit annoying. It's okay, we'll do it. These s's cancel out. Looks like that negative t minus t turns into negative 2t. We'll have negative 2t minus, we'll distribute that, 2s squared plus 4t s plus 2t squared. I'm sorry if I lost you on this. Minus, we added those up already, plus s squared plus 2ts plus t squared. Let's see, doing all these together, we have negative 2s plus s, that turns into negative s squared. 2t squared plus t squared is going to equal 3t squared. Our 4ts plus 2ts is going to equal 6ts. It looks like we're just left with that minus 2t right there. And it looks like that is what our partial is going to be for for our dz dt. Let me make sure that's right. That looks about right to me. I mean, I don't see a problem there. Worst case, I made a little bit of an algebraic error. Point of the story is, that is how the chain rule is conducted. That last example was a little bit messy. I apologize for that, but you get the idea. That is the chain rule. Thank you very much.